Okay guys, so let's continue our topics in the robotics. And in the previous class I taught you about the DH parameters, the Navitt-Hunterberg parameters, because I taught you it's very important parameters in robotics. Any published robotic papers, if you want to go to real robots, you have to know the DH parameters, because eventually we're going to use this in the Jacobian and the derivation of the equation of the motion of the robot. Okay, so let me do another example in addition to the part 8. So suppose that you have such a robot. Look at here. The robot has, hold on. Okay, so this is the robot. We have a rotation around this axis, okay? And then this is rotating, that's right? So then I have a link here, but so all of these, they're rotating like this. See, this is one link of the robot. Another link is prismatic, so it's moving up and down. That's right. So they are moving like this. Okay, they are moving like this. Okay, and then we have this link of the robot. Okay, that is moving like this. In this direction. This is prismatic again. So we have one rotational, one prismatic, two prismatic, and this connects to the end effector. Suppose here's end effector. So we're gonna derive the DH parameter of this robot. Okay, let me see if it's recording. Yeah, so what we're gonna do, we're gonna simplify this to our famous. So we're gonna say this is equal to, okay, it's equal to this robotic system. This is a revolute joint. Okay, then this goes to this prismatic joint. This prismatic joint, right, which moves up and down. That's right. And we say here is D1. Say here is D1, and here is D2, means changing, is going up and down. So this length of this link is D1, and then this continues to this prismatic joint. Here we go. But this moves in this direction, right? So here gonna be D3. There we go. And this connects to end effector. Here is end effector. Okay? So what we're gonna do first, as I taught you, we have to set up the coordinate system. Because this is prismatic based on the rule I taught you, the z-axis always is in the direction of the rotation. So here gonna be what? Z naught. And respecting the right hand rule, this is gonna be what? Rotating at theta 1. I told you this star means the theta 1 is changing with time. That's right. Clear? And also because this prismatic joint goes up and down, that's right. So Z1 gonna be again, as I taught you, in the direction of the translational motion. So this is gonna be Z1. Clear? But this moves in this direction, horizontal. This is going to be what? Z2. And obviously this is an effector because moving at the same direction of that. This is going to be Z3. Understand? So as I told you, the X naught, okay, gonna be the line that is connecting the Z naught to Z1. Okay, and you can say here arbitrarily, because you see that X naught is normal to this page of Z naught and Z1. That's right, Z naught and Z1. And so by right hand rule, this is gonna be Y naught. So X1 must be normal to Z naught and Z1. That's right. Remember that the previous class I was teaching about the Navitt-Hunterberg and fixing the coordinate systems. That's right. So this is gonna be also out of the page. This is gonna be X1. That's right. Right hand rule, this gives you Y1. because x1 is connecting z1 and z0 and is normal to both of them. Remember? So x is connecting the zi minus 1 to zi. Go and read the part A of this course, and it's normal to both of them. Understand? With the minimum length. Okay? So, and now again, x2 must be normal to z1 and z2. So again, out of the page. It's going to be out of the page. That's right? Normal to both of them. That's right? Going to be x2. That's right? So by the right hand rule, y2 gonna be in this direction. Let me redo it because I'm gonna do too many things here. And obviously this is z3, z2. So x3 gonna be again out of the page. This is x3. So again, right hand rule gives you y3. So now we set up the coordinate system attached to the joints and links. That's right, obviously. So how many links we have? How many links we have? We have, this is base. So we have 1 and 2, 3, 4. That's right. So we're gonna have 3 links. That's right. This is the first link. That's right. And second link, and the third link. That's right. Third link. So now we can now make our DH table. DH. Look at here. This is link number. We have 3 links. 1, 2, 3. So what we have 4 DH parameters. Alpha I, let me start with I, alpha I, di, and the theta I. Remember? So the I, remember, was the distance along this x-axis connecting z1 to z2. So along the x0 axis, so what is the distance between z0 and z1 axis? Along x1 axis, obviously is how much? 0, because x0 is out of the page. So along that axis, distance, the line connecting z1 to z0 is 0. So distance between z1 and z2 along with the x1 axis, right, again is, because x1 is out of the page, right, it is 0. Clear? Now distance between the line between connecting z2 and z3 measured along the x2 axis. X2 axis is out of the page again, so it's gonna be 0. Understand? Alpha I was the angle between the z's measured about the x-axis. So what is the angle between z0 and the z1? They are parallel lines. So what's the angle between them? 0. Angle between z1 and z2 measured around the x1 axis. x1 is out of the page, guys. I'm plotting here. Look at here. See here, this is x1. This is z1, and if I transfer this z2 to the origin of here, look at here, z2. So if you put your thumb on the x1 axis, your 4 fingers rotation shows this. That's right. Here is positive side. So but we want to know from the DH parameter the angle between z1 to z2 along the x-axis. So what you have to do, you have to put your thumb in opposite direction of the x1, that's right, and shows this direction, that's right. So here gonna be negative how much? Negative how much? Negative 90 degree. minus 90 degree. Clear again? Look at here, guys. This is, we want to find the angle between Z1 to Z2. That's right. About the x-axis, x1 axis. If you put your thumb on the x1 axis and the fingers shows this rotation, so it is positive. That's right, right hand rule. But you want to find this rotation, reverse direction. That's right. So your thumb must be in the negative side of x1. So it is minus 90. Clear? Now the angle between Z2 and Z3, they are the polar lines. That's right. Gonna be 0. Understand? So let me go to theta. Theta is what? The angles between x-axes. Remember from the part A, theta is angle. Let me write here for refreshing your mind. Alpha i's are the angles between z-axes. Theta is angle between what? X-axes. X. Understand? So, hold on. Okay, so, but this is angle between z-axes about xi minus 1 axis. This is about z. Okay, so I want to see the angle between x0 to x1 along z0, zi minus 1. Around z. Look at here. I'm plotting here. So this is x0. This is x1. They are exactly parallel. So along what? I'm measuring around the z0. Put your thumb on D. So there's no angle because they are parallel. So this is gonna be how much? Oh, sorry. I'm stupid, guys. I'm getting older. So because this is rotating, that's right. This angle is rotating. See? So if I put this here, x0, but after, because of this rotation, this x1 is rotating like this. That's right. This is gonna be x1. That's right. This was the original x1. So z0. Understand? So if you wanna rotate from x0 to x1, you put your thumb on z0 and the forefinger shows that angle. So how much is that? Is theta 1. So here gonna be theta 1 star, because x1 is rotating because of rotation in this joint. Clear? Again, I'm explaining. This is your x0. This is your original x1. But after rotation subject to this angle of the revolute joints, this comes to here. So angle between x0 or the old x1 and new x1 gonna be this angle. Obviously, it's like that. And okay, now the angle between x1 and x2 along what? Z1 axis. Along Z1 axis. I'm plotting here, guys. So, guys, when this rotates, this also rotates, because this is on this. That's right. So look at here. This is x1, x2. Because of this revolute joints rotation, the both of them rotate. So the both of them comes here, the new positions. This is gonna be x2 and the x1 around what? Z1. Because they are rotating together, so it's gonna be 0. Understand? And again, because this rotates and this rotates, also this rotates, because they are connected. That's right. This is on this. They are coupled. That's right. All of them, they are moving up and down, but they are coupled. So here gonna be also 0. Understand? Now what is di? What is di? A distance between the origins of the frames. Distance between the origins of the frames. Simply, this is distance between origins of frames. So here is D1. This moves up and down for distance of varying D2, and this moves in this direction for distance varying of D3. That's right, I told you. This star, okay, this superscribe star means changing with time. Okay, now I give you 2 minutes to think that what are the DIs I will teach you. Don't go ahead because you are learning. Okay. So this is between origins of the frame distance. Okay. Obviously, distance between the origin of this and origin of this is how much? Is D1. Distance between the origin of this frame and origin of this frame, because this moves up, okay, this moves up, okay, gonna be D2. Between the origin of this and origin of this is changing with D3. Understand? So here is fixed. Here is fixed. Here is fixed. This only moves up and down. This only moves up and down. Okay. So the distance between D1, D2, and D3. So this is the DH parameter of this robotic system. This robotic system has 3 degrees of freedom. What are those 3 degrees of freedom? Angle theta 1, displacement D2, and displacement D3. Oh, I don't know what's happened. D3. These are the degree of freedom of this robot. This rotation, this motion, and this motion. Okay? Now, for this system, if I tell you calculate the transformation matrix between end effector 3 and 0, you know that you have to say A homogeneous transformation of A1 with respect to 0, A2 with respect to 0, and A3 A2 with respect to 1, and A3 with respect to 2. Right, so hold on guys, I have to fix it. Okay guys, so A3 with respect to 2, hopefully this works. A3 with respect to 2. Now let's do together, huh? So A1 with respect to 0. Again, this homogeneous transformation 0, 0, 0, 1. Now look at here. Frame 1 with respect to 0. Frame 1 is being rotated because of this rotation. So I'm putting here guys, look at here. So x naught, here we go. This is x naught, y naught, and the z naught. That's right. So because of this rotation around the z axis, z naught axis, the rotated form of, I'm changing the color, it's gonna be like this. X1 gonna be planar, Y1, and the z1 is on this because the z direction is not changing. That's right. So this angle is theta, this angle is also is theta, and they are on the same plane. These are at the same plane. So as you know now, it's going to be cosine theta, sine theta, and 0, and the y going to be what? Minus sine theta, cosine theta, and 0. And because the direction of the z1 is not changing and is aligned with the z0, you're going to have 0, 0, and 1. That's right. But the origins of this frame has an offset with the origins of this frame. That's right. How much is the offset? Yes, it is d1. This is d1. That's right, it's fixed. So this is d1 is fixed. So in which direction? In direction of z. So it's going to be 0, 0, and d1. Understand? Clear? Okay. Now let's go to A2 respect to what? As I taught you, a frame 2 and frame 1, let me draw it here, guys. This is 1, x1, y1, and the 0. They are rotating together because they are at the same length. That's right. So you're gonna have this. I'm transferring the frame 2, transferring the frame 2 on this. I'm picking this. So this is gonna be y2. Here gonna be x2. Here gonna be z2. Right? For the angle of how much? Theta again. Clear? Understand? So these are at the same plane. These. But the y2 is in the opposite direction of z1. Understand? Oh, I made a mistake. I'm saying that I'm plotting stupid things. So here is this is x1. I just want to show this is rotating. So and so because they are rotating together, this is going to be x1 and 2. This is going to be y1 and z2. Understand? And this is y2. I just want to show that they are rotating. Okay. So because they are rotating subject to the rotation angle of theta 1. See, they are at the same length. They are rotating together. Understand? Maybe I misplotted this, but this is obvious. So they are at the same. They are rotating together. That's right. So x1 and x2 gonna be the same. z2 and y1 they are on each other, but the y2 is in opposite direction of the z1. So what we're gonna have is this. Again, 1, 0, 0. We know always this is here. See, x2 over this x2 over y1, and this is obvious. So y2 but is in the opposite direction of z1. So y2 must be expressed like these guys. Minus 1, 0, and 0. Because y2 is in the opposite direction of, look at here, y2 is in the opposite direction of z1. y2 is in the opposite direction of z1. Now z2. z2 is aligned in the same direction of y1. So you're gonna have 1, 0, and 0. Now the origins. Origins of this and this. Origin of this is being moved distance of d2. That's right. It's going up from this fixed point. Here's fixed, as I told you. Okay, here's fixed. It's going up and down d2. That's right. In which direction? In the direction of the z1. So, hold on. So it's gonna be 0, 0, d2 multiplied by the third homogeneous transformation, 3 respectively. 0, 0, 0, 1. Okay. Now, again, see, they are exactly all of them the same directions, and this is rotating with this because they are coupled. That's right, subject to the one. So you're gonna have unity matrix because they are rotating to each other. 1, 0, 0, 0, 1, 0, 0, 0, 1. Identity matrix because they are rotating to each other. About the distances of the origins, this is being moved from this for D3. Which direction? Z2. Here we go. 0, 0, D3. So you can find it. Please do it at home as homework for yourself. Okay? Please do it as homework for yourself. I don't want to waste your time more than this. Okay? So after knowing the Denavit-Hartenberg parameters, now it is to teach you the most important topic, one of the most important topics in the robotic, that is Jacobian matrix. Jacobian matrix. Here we go. Let me see. So if you remember the first class, we already calculated Jacobian as this, remember, x dot was j theta dot, and we defined the forward kinematics and inverse kinematics. Forward kinematics when you have theta dot and you are calculating x and the x dot, and the factor what? Positions and orientation. This is forward kinematic. But the inverse kinematic, if you remember, that we defined as when you have this, you have the end effector position, and then you are trying to find the links joints. This is inverse kinematics. How? By saying theta dot is the inverse of the Jacobian in x dot. Remember? But this is was for the two links. When we have a 7 degree of freedom, like a Baxter I showed you in my lab, or we have the NAO humanoid robot that is 25 degree of freedom in my lab, or we have a quadruped that is 18 degree of freedom, that is a dog robot. Also Boston Dynamics has it. So this is not this. We need a classical and strong approach to calculate the Jacobian matrix, that is relating the angles of the links, angular velocity of the links, to the position and the translational velocity of end vector, and vice versa. Depends on that you want to do forward kinematics or inverse kinematics. Okay, so now you have to know some basics. We need the deep mathematics here. Jacobian is a 6 by n matrix, has 6 rows always and n columns. How? N is the number of joints. Okay, so we know that Jacobian that we want to calculate for any robot is a 6 by n matrix. So obviously, suppose that I have a 6 degree of freedom robot. 6 degree of freedom robot, like this. 1, 2, 3, 4, 5, and 6. So that's right. 1, 2, 3, 4, 5, 6. Up. That's right. 6. right? 1, 2, 3, 4, 5, 6. That's right. This is in the vector. Huh? I have a 6 degree of freedom. Say this is planar robot. This is theta 1. This is say theta 2 rotating. This is theta 3. This is theta 4. This is theta 5, and this is theta 6. See, rotation like theta 1, theta 2, theta 3, theta 4, theta 5, and theta 6. So you have 6 joints. So your Jacobian matrix gonna be 6 by 6, or is a square matrix. Okay, but we have another definition in robotics. We say redundant robots. We say it is redundant robots. What is the redundant robot? Baxter in my lab, as I showed you, is a redundant robot. Means number of joints is simply more than number of degree of freedom. Okay. So if you look at, let me show you, because it's a little confusing guys for you. If you look at this, so guys, this is Baxter, right, in my lab.
This
Show. And can I stand up, robot, for them? Stand up? Yeah, good.
This robot has 7 joints, but the end effector that want to seize or capture object in space has what? 6 degrees of freedom, 3 rotations and 3 positions of the object. That's right. So I have 6 degrees of freedom robot. This is not degree of freedom. Means the robot number is more than the number of coordinates. Coordinates. Okay. Not degree of freedom. So an object in space has 6 degrees of freedom. One of them is 3 rotations and 3 what? Translational motions. For the Baxter, the number of degrees of freedom of Baxter is 7 for one arm. So 7 is higher than 6. So you have 1 degree of redundancy. So what's the advantage of that? Redundancy, let me write it down. Redundancy gives more flexibility. So the Baxter in the lab that you saw has 7 degrees of freedom. I have 7 joints for the Baxter to be actuated. So the Jacobian of the Baxter gonna be 6 by 7. What is the take-home message? Its Jacobian is not square. And you're gonna say, what the point of that? I will teach you that the inverse of the Jacobian that we use here, it's not normal inverse. You have to use pseudo inverse. I'm gonna teach you. Okay, the pseudo inverse. Understand? So on the other hand, when we write x dot is equal to j Jacobian in theta dot, will mean that, as I said, we have 3 rotations and 3 positions. So you have x dot n of n effector that you want, because at the robotics and n effector grabs the object. So the n effector has 3 rotational component and 3 what translational component. Together gonna be 6. Right? So 3 rotational and 3 what end effector for omega. That's right, omega. So on rotational it's equal to Jacobian and theta dot. That's right. So this is for end effector, this is for the links. Understand? So now you understand what I'm talking about. For the Baxter, this is how much? Gonna be end effector 6 by 1. For Baxter, Jacobian is 6 by 7. But Baxter has 7 joints, so this is gonna be 7 by 1. That gives you 6 by 1. Understand? You see that the Jacobian is not square here for the Baxter. Understand? So, but for calculating the Jacobian, we need deep mathematics. The first things that you have to know is SQ symmetric matrix. You have to know what is the SQ symmetric matrix. Remember, in the rotation matrix, we know that is orthogonal. If I refresh your mind, R transpose is R inverse. Remember, this is orthogonal matrix, and the columns of the rotation matrix value, that's right, depends on the dimension of that. The value is 1, and the columns of the rows of the C and Z, they are normal together. That's why we say the orthogonal matrix. That's right. Now you have to know SQ symmetric matrix. SQ symmetric matrix, a matrix S is said to be SQ symmetric if and only if S transpose plus S is 0. This is the definition of SQ symmetric matrix. So on the other hand, because this is the matrix, so has what? Elements. On the other hand, if you have Sij, ith column and j ith row and j column of S plus its transpose, going to be Sji, that's right, transpose is 0. Or you can mathematically say Sji is equal to minus Sij. Understand? Or this is for non-diagonal elements. For diagonal elements, you're gonna have Sii, this plus its transpose, gonna be again Sii. The transpose of this is gonna be the same, gonna be 0. So Sii is how much? Is 0. For SQ symmetric matrix, this is another property for that. Diagonal elements are 0. Non-diagonal elements are what? They have inverse sign. That's right. So this is for diagonal elements. This is non-diagonal. This is for non-diagonal elements. Understand? So, on the other hand, this is general statement for the SQ symmetric, because based on this lesson, diagonal elements of SQ symmetric matrix is always 0, and non-diagonal gonna be minus S3. This gonna be S3. This gonna be S2. This gonna be minus S2. This gonna be minus S1. This gonna be S1. If you have a matrix, if you have a SQ symmetric matrix, you have to always write in this format. Always. Let me give you an example. Suppose you have a matrix A, okay, and it is AX, AY, and AZ transpose. So if I say find SQ symmetric form of this, you're gonna say S of A, SQ symmetric form of this vector A, gonna be 0, 0, 0, minus S3, third component, minus AZ. Now here gonna be AZ. S2, second component, gonna be AY, the gonna be minus AY. Exactly like this. Exactly like this. And the minus S1, minus AX, and here is AX. Let's do another example about SQ symmetric matrix. So suppose that you have a unit vectors I, J, K. Okay, you know that the unit vector in I direction gonna be 1, 0, 0. That's right. If I say find the SQ symmetric form of I, gonna be how much? Again, 0, 0, 0, starting from here to here. That's right. Gonna be 0, 0, 0, 0, and here gonna be minus 1 and 1. Look at here, minus S1 and S1, minus S1 and S1. So here gonna be again how much? It's gonna be minus 1 and 1. If I say find S of J, unit vector J, so it's gonna be how much? Again, 0, 0, 0. So we know that the J is how much? 0, 1, and 0. Starting from here to this direction, 0, 0, and here I give you 1, minus 1, 0, 0. Look at here, guys. S2 plus minus, S2 plus minus, or we know that the K is how much? 0, 0, and 1. So S of K, SQ symmetric form of the unit vector K, is again 0, 0, 0, minus S3. In this section, minus S3, minus 1, 1, 0, 0, 0, 0. Understand? So this is how we define SQ symmetric matrix. So I'm gonna teach you the rest on the next class.